Okay, so today we're going to be re-going over vector fields, and hopefully we'll have time to talk about work integrals at the end of the period. Okay, so let me just remind you, remember a vector field can be either a vector field in the plane or a vector field in 3D. And they're a vector, so they've got components. And the components are functions. So sometimes write P of xy, Q of xy in the 2D case. So two components with two inputs. Or if you're in the 3D case, you'll have three components, and each component is a function of three variables. So P of x, y, z, Q of x, y, z, and R, P, Q, R, x, y, z. And these are oftentimes really pretty to graph out. They're really nice things to look at if you have Mathematica on your computer. I can tell you all how to get Wolfram Alpha to plot some basic vector fields, at least 2D ones. So let's do an example. Let's say v of xy, so we're doing a 2D one, is negative y comma x. So this means my p of xy is just the function negative y, and my q of xy is just the function x. Okay, so let's plot this. So I'm going to have my coordinate axes right here. And well, I'll want to plot the vector field at some different points on my axes. Okay, so let's plug in a few of these points. This is the point, let's say 1, 1. So I'm going to make a table. I'm going to write the x, y, and the corresponding v of x, y. So at the point 1, 1, well, let's look at my formula right here. I have to flip them. The x component goes to the y component goes to the x, and then I negate the first component. So if I flipped them and negated the first one, I would get negative 1, 1. So let's plot that vector starting at the space point and moves up in that northwest direction. Let's plot another one. Let's do the point right here. That point right there is 0, 1. And to figure out which vector I'll have at that point up there, I plug into this thing. So in this specific vector field, I flip them and I make the first component negative. Again, I'm looking at this right here because, okay. So this is negative 1, 0. And that's a vector that points straight to the left, no vertical component. then we've got, let's say, negative 1, 1, which is then this next point. Again, I've got to flip them and make it the first component negative. So if I flip them and make it negative, the first component negative, I'll be looking at negative 1, negative 1. And this point's in the southwest direction. I'll do one more, and then we can kind of fill in the rest with what our gut tells us to do. Finally, let's look at this point right here. That point right there is negative 1, 0. And the corresponding output is negative 0. Well, that's just 0, negative 1. And that's going straight down. And you can see that what this does is if I fill in the rest, it sort of makes this rotational vector field. And if I wanted to fill in other ones, it would do the same thing. So we call this this is like a rotating vector field. It's not a technical term, but it just looks like sort of a hurricane from a bird's eye view. Rotational vector field. Okay. Does anybody have any questions about how we plotted the points, how we got the red vectors? All came from this formula right here. If there aren't, I'm going to move on to the next. I'm going to do another example. I'll do one in 3D. All right. So let's do another example. It's a pretty big one, but I wanted you to see. So this is plot the 3D vector field. v of x, y, z is just 1, 1, 1. Okay, this is pretty boring vector field. It's a constant vector field. And I don't really need to do that table that I did on the previous page because it's so easy. Every point that I could possibly plug in, so all these different points in 3D space, I want to attach a vector whose base point is at that point. And the vector doesn't even change with where I am situated. It's always this, right up, this northeast up vector. So this thing right here at every single point. I think it's like a flat vector field. The vector field really isn't that interesting. It's a constant vector field. But I just wanted to kind of show you, what you can get in 3D. Let me show you another more interesting example. So let's do v of x, y, z is okay, the x component. So I'm going to go back to example 2. Really, this means p of x, y, z was 1, q of x, y, z was 1, and r of x, y, z was 1. That was what was happening up there. Coming back to this new example, I got to tell you what my p, my q, and my r are. So my first component is x. This is my p. My y component is y, q, and my z component is z. This is r. So it's kind of this nice case where my x component is actually equal to the x variable itself. It doesn't always have to be this way. Like this component doesn't always need to be x. I mean, remember over here, the x component was a negative y. So, don't think that every vector field has to only have x's right here, only have y's right here, and only have z's right here. That would be wild. Okay, but let's plot some points. So let's look in our 3D axis, our three-dimensional space. Okay, let's plot the vector at the red point, the green point, and let's do a purple point. Okay, I'm not going to need to make a table because this is so basic. I mean, if I plug in the red point, it's 1, 1, 0. Sorry, 1, 0, 0, and that just the corresponding vector is 1, 0, 0, which points directly out to the right. So if I do that in red, that'll be coming out exactly to the right. If I look at that green, which is 0, 1, 1, sorry, 0, 1, 0, the vector that's whose base point is sitting at that point is 0, 1, 0, just coming right out of the right backwards, and this is going to come right up. So in fact, if I plotted 1, 1, 1, which would be maybe right here, the vector field evaluated at that point is kind of coming right in that upper northwest or upper northeast direction, just like what was happening in the previous at that exact location. And this is, if you plot any point, it looks like the vector that's extending radially out from the origin. So we kind of call this one a radial. This is a radial vector field. There are some that should be coming at your face and some that are going away from your face. It's in 3D. So we call this a radial vector field. It's because it's emanating outwards from the origin. And you should maybe remember what we talked when we did a similar example at the end of class on Friday. Remember we had v of xy just in the plane was x, comma, y. And this looks like, again, it looked like the vector fields all emanating out from the origin. So note the similarities between, I'll use my highlighter, between that vector field and this vector field. Okay. And the similarities in the corresponding pictures. All right. I'll do another example and then we'll talk about something kind of interesting. Not that this isn't interesting, but let me just kind of find, or let me at least say, a 2D vector field may be extended. I'll label it. I'll label a 2D vector field V equals PQ. So it has components P and Q, may be extended to a 3D vector field by making the Z component, which is, just R, equal to 0. So an example was when we had that rotational vector field. I'll repeat it right here. We had V of xy was negative yx. This was our first example of the day. This was our P, this was our Q. I'm going to make it into a 3D vector field by just making that last component dead 0. And I'll draw a brief little picture of what we got on the first page. That was our rotational vector field, our first example of the day. Now, how does this look? So now to plot this, what you'll do is you'll take this 2D picture and stack a whole bunch of them on top of each other. Let's just think about why that makes sense. So here will be my axes, X, Y, Z. I'll draw the vector field. I'll do it with different colors. So here's kind of in that Z equals 0 plane. It looks like some rotation like this. Really, it's in a 2D plane. All the vectors are tangent to that flat plane. And then a little bit higher up, the picture doesn't really change so much. It's, again, just rotation in that plane. And so if I kind of want to fill in the vectors in other places, it's at whichever plane it's in, it's always tangent to that plane. So it's kind of, think of this would look like if you could see the wind of a tornado or a cyclone. Where would the arrows be pointing? They kind of cycle around this vertical axis. That's a good example. And another example would be V of x, y, z, extending that radial vector field on the previous page. So let me show you. We're going to be extending this thing by just plugging a 0 at the last component. So x comma y comma what now? 0. And that will just do the same thing, meaning we'll have our x, y, z, and in that flat plane, we'll be emanating outwardly from that from the origin right there. But if we moved up a little higher, maybe at z equals 1, we would just be emanating outwardly from 0, 0, 1. And all the vectors in 3D space, if you want to pick at any random point, you figure out what z value it is, and you'd be just moving outwardly from it. Kind of like this. Just remember, a vector field is at every single point, it's a way to make a vector at that point. Okay. All right. So I'll move on to this next page and we'll talk about something a little bit different. So I want to remind you that this is something that I said on Friday, that you've actually dealt with vector fields before. We've looked at the gradient vector field. So remember, some vector fields are the gradient of another function. Meaning, if I hand you some v of xy, it might turn out to be the gradient of f for some f. That is, if I write out what the components are, that means PQ is, there's some function for which if you take the x derivative, it will equal the P, and if you take the y derivative, it will equal the Q. This is kind of restrictive. like maybe a function exists like that, or maybe it doesn't. But let me just remind you a good example. So an example was the radial vector field. V of x, y is just x comma y. This was this one. If I look at the function, if I consider f of x, y is 1/2 x squared plus y squared, then partial f partial x is, well, I got the 2 explicitly there to cancel in the power rule, so I just get x. Partial f partial y is y, so this means that the gradient vector field is x comma y, but lo and behold, that's the thing I originally started with. So this actually turns out to equal v itself. Okay, so v is special in this case. So when I first, so it's kind of like, I'm going to say it this way, v has a parent. That is, v like comes from something. There's an f whose gradient produces v. So when I first learned about this stuff, the professor was use an English word that I didn't know. So I'm going to pass this lesson on to you all. So maybe you all know this. There's a good chance that everybody knows this word, and I just didn't, and I'm a fool. But there's this English word called vestige. And I actually looked up the definition last night, and it says a trace of something that no longer exists. Okay, it's a noun. And when my professor first taught me this, they used the word language, this noun vestige, and they said v is a vestige of the function f. Really, it came from an f. It has a parent. Okay, so in this case, we say that so none of this was math. None of this was math language. But I'll say what it is in math language and how you'll see it in real life now. We say that f is a potential function for v. I think potential, think P stands for parent. Okay, so in this case, in this radial vector field right here, I'll arrow it in purple, this V has a parent. Okay, not every vector field has a parent though. Okay, so I'm going to write that in this next page. Not every function, so not function, and not every vector field V has a parent, or that same thing as potential function. Okay. So let us, is 1 plus 3. So to determine if a function, and this is going to be a really important thing, to determine if a vector field has a potential function, that is, if it's a gradient of some other function, there's a tool that we can use to quickly check. Okay, so this is a definition. Given a vector field equals PQ, define the curl of V to be, you should think of it as the determinant of partial x, partial y, P and Q, this 2 by 2 determinant. So this is kind of in quotes because it's not quite right, because it's not a vector. This thing isn't a vector here. These are operators, but this is how you'll set it up every single time. It's kind of it's a little trick. I mean, it's a mnemonic almost. So really, it's like you take a partial derivative of Q with respect to X, and then you subtract a partial derivative of P with respect to Y. So this is partial Q, partial X, minus partial P, partial Y. This is called the curl of V. All right. Let's do a really quick just computation of this. Again, this is like on the first weeks of class, I taught you what the dot product was, and I said, I don't expect you to have any understanding in your bones yet about why this is significant, but now everybody knows how significant the dot product is. I don't expect you right now to have any feeling for what this thing is, but sooner or later we will. So let's just compute an example. And I promise we'll come back to this top point, this thing about vector fields not having a parent. That's kind of what the rest of this class is all about. All right, so example, if V is that rotational vector field, this was minus y comma x, and I'll draw it really quickly. It's the hurricane from above. If that's my vector field, compute the curl of V. All right, so this is going to be, I'll set up a determinant, partial x, partial y, and this was my P, that was my Q, and that was this piece. Okay, that was this piece. Okay, so we've got negative y and x. So I've got to take the x derivative of x, which gives me 1. And I've got to subtract the y derivative of negative y, which gives me negative 1. And this gives me constant 2. Okay, so it just turns out that sometimes this thing can depend on x and y. It can be a function, but in this case, it's just a constant function. So this can depend on x, y, but in this case is constant. Okay, so let's do a second example of a computation. Let's do example V equals the radial vector field. So x comma y, and this is everything spits out radially. And let's do compute the curl of V. So again, this is a determinant of partial x, partial y. I'm going to skip out on the colors. But now, well, we've got x derivative hitting a y, so I've got 0, minus y derivative hitting an x, that's also 0. And so this is 0. Again, it's a constant function. So these are just two quick examples of computing the curl of a 2D vector field. Now I'm going to tell you why it's significant. Okay. So I'm going to move to this next page. So here's one application or significance of curl. It's an easy way to quickly check if a vector field is a gradient, meaning, i.e., if a vector field has a parent, or if it's a vestige. of a potential function. So let me run a quick experiment in front of y'all. So let's suppose v equals p comma q is equal to the gradient of some function. So this is suppose a vector field does have a parent. So for example, we could look in this previous case, we'd be talking about certainly this one right here. That one has a parent. It comes from that x squared plus y squared thingy bob I said on a couple pages back. So suppose we're in the case where a vector field does have a potential function. So this tells us that p is the partial derivative of f with respect to x for some mystery f. I don't know what the f is, but we're supposing it exists. And q is partial f partial y, again, for that same f. So let's compute the curl of v in this case. This is the determinant of this thing. We've got p and q, but I can replace these with partial f and partial y. So partial x, partial y, partial f, partial x, partial f, partial y. And we're going to see what happens. What did I use on the previous page? Okay, so this hits this, and this hits this, and I've got partial squared f, partial x, partial y, minus partial squared f, partial y, partial x. Okay, now can anybody see or write in the comments what this thing will simplify to be, even if you don't know what f is? Yeah, that's right. It's 0. It's 0 because the mixed partials commute. Perfect. Yeah, it doesn't matter if you do an x derivative first, then a y, or a y, then an x. They're the same thing. So these things are equal. And whenever you have x minus x, you just get 0. So this is 0. So the lesson, the takeaway is, thus, if a vector field has a potential function, then its curl better be 0. If the curl of v is not 0, then it does not have a parent. So then it is not a gradient vector field and does not have a potential function and does not have a potential function. Okay, so I'll write that rule. I'll write a definition on this next page, and I'll say, so definition, let v, p, q be a vector field. Then if the curl of v is 0, we say either v is curl free, or we could also say v is a conservative vector field. This has nothing. This is nothing to do with the political statements at all. This is we'll see that this has something to do with integrals later, and there's a conserved quantity along path integrals, but we'll see where these things come from. Okay, so these are equivalent definitions. Okay, so this immediately tells us, we know that because the curl of negative yx, this was our rotational vector field, this is not 0, so negative yx is not conservative, and so it does not have a potential function. Okay, because we got that, we computed on the a couple pages ago that curl was flat 2. So it couldn't, like, by this reasoning, if it did come from a potential function, then in the process of taking a curl, this mixed partial thing would happen, and we would have to get that the curl was 0, but it's not 0, so it didn't come. It doesn't fit into this structure right here. In a sense, this is a restrictive condition. There's a reason why not every vector field satisfies this condition, and it's because it's you sort of lose degrees of freedom by requiring that P and Q come from only one choice of F. It's like P and Q, you can pick too many random functions, but picking a gradient vector field is only a choice of one function. So you can you have more fluidity in picking a PQ, but I'm kind of saying more than I need to right now. So let's do some more examples. Where's my page? Okay, let's do an example. I'm going to say V of x, y is equal to 2xy cubed, comma, 3x squared, y squared, plus 1. All right. So let's first compute curl. Okay, this is going to be a determinant. 2xy cubed, 3x squared, y squared, plus 1. Oof, that's ugly. Okay. And if I just do some partials, the x is going to hit this, and I'll get, I guess, 6xy squared plus 0, because that's a constant, minus this derivative that I take from y. So if I take that derivative, that 3 comes down from the y, and I get 6xy squared. Okay, what's happening? I've got some sort of cancellation. Like, the mixed derivatives actually agree. So this tells us that V is curl free, or V is conservative. Okay, so there's a chance that V has a potential function. V might come from an F. Okay, so thus V might be might have a potential function F. This would mean we would have, so let's start looking for an F. Okay, so let's investigate what might this F look like. Okay, so Daniel asked, just checking, curl equals 0 does not necessarily apply. Oh, that's a really good question, Daniel. Okay, yeah. Okay, so we're gonna let me put a pin in that. So I'm gonna put a pin in Daniel's question, but Daniel's definitely onto something. So the implication is that Daniel's getting at is this: if potential exists, potential function f exists, then, so math people say this double thick arrow means implies. So we've definitely shown that if a potential function f exists, then V is curl free, or curl of V is 0. But Daniel's asking the other way. So if curl of V equals 0 does it necessarily imply that a potential function exists? So I'm going to put a pause on this, and we'll talk about that later. But this is sort of like, I mean, the sort of logical structure is like, if it's a if it's a mammal, is it a cat? Is it a cat? If it's a cat, is it a mammal? Or like, if the series diverges, sorry, if the terms go to 0, does the series converge? If the series converge, do the terms go to 0, kind of thing? Okay, so we'll put a pause in that. But in this case, we're going to see that this vector field, I'll write it on this next page, does come from a potential function. So let's see. So again, this is v of x, y is, I'm just copying and pasting from the previous page. It might be on your notes still. Oh my gosh. Okay. 2xy cubed through, okay. 2xy cubed, comma, sorry, 3x squared y squared plus 1. 3x squared y squared plus 1, giving everybody car sickness. Okay, so let's, if this were the case, if v were equal to the gradient of some f, which we're checking for, then we would have to have that 2xy cubed would be partial f partial x for some, this is what we would have to have for some mystery function f. So if that were the case, we could integrate both sides with respect to x, and the left-hand side would be x. Okay, so what we would have is I'll organize my thoughts differently. In this case, f of xy would be the integral of 2xy cubed dx, indefinite, so we need to add some constant. If that were the case, then this would be the case. But it's not quite just a constant. It should be a constant function with respect to x. So in this case, we would really have not just a constant, but a constant function of y. Okay, so let's do that integral. Let's do that improper integral, not improper, indefinite integral. We're just going to pop x up by a power of 2 and divide by 2. So we would have to have f of xy is x squared y cubed plus, I don't know, some other function of y that we don't quite yet know. But we can sort of figure out what it might have to be. So on the other hand, we can do it with the y's. So this would also mean f of xy would be the integral of my q piece plus some other constant function of x. So to find what goes in this integral, it's my q, which would have to be partial f partial y. And so let me just copy and paste. This is 3x squared y squared plus 1. If I do that integral, I'll get x squared y cubed plus y plus, again, some constant mystery function of x. So if I'm to have any luck with figuring out what f of x is, I've got to look at these two different boxes, and I have to identify who is playing the role of whom, I guess. I guess that's the right way you say that. So I'm looking in the top box and the blue box, and I want to say who is who. Okay, so Joe asked a question to me privately on accident. So Joe asked, could you just substitute in the partial, sorry, maybe I shouldn't have said this out loud. Sorry, if you wanted this to be private.
No, that was a mistake, my bad.
Okay, so Joe said, go ahead, yeah, just say it out loud.
Like, could you just take the pretty function y, could you just take the partial with respect to y and then solve out, since we already for the constant?
Solve it out. I mean, I think we might be doing, I'm about to do, maybe you'll see I'm doing the same thing you're suggesting. Let me substitute in the partial y that we already have.
3x squared y squared plus 1 equals 2, and then take the partial.
Sorry, Joe, sometimes you cut out a little bit, and my computer can't hear you very well at times.
It's no problem.
Okay, yeah, maybe see how I'm gonna do this, and then if that doesn't answer questions, let's check after class. Okay, so I've got to look in these. I'm seeing this thing agrees with this thing, so that's cool. I got to figure out what my C and like what my K are. So up here, I'm seeing I've got some constant function with respect to. Oh, I'm frozen again. Okay, stop mirroring. Okay, this happens if I talk too long. Okay, so I'm looking at those two boxes, and I'm seeing those yellow pieces are going to agree. And I'm seeing I've got this constant function of y. What could that be? What could that correspond to in that lower box? Ah, I see a constant function of y right there. And then you're like, well, I need to have a constant function of x somewhere, but you can just make that 0. So my full function is my orange plus my purple plus my peach. So the function is x squared y cubed plus y. This is one function that would work. You could also add a different constant. You could also also add 6. That would also work. But I could verify for you that if you took partial derivatives of this thing, you'd actually get that the vector field v is the gradient of f. Okay. So in this case, v has curl 0 and actually equals the gradient of some function. It has a parent. It's a vestige. It came from something. Okay, so let me look. This was page 5. Where is my page? 6. All right, I need to quickly. This was page 7. Here's page 8. I need to quickly talk about the curl of a vector field. I need to talk about the curl of a vector field of 3 variables, of a 3D vector field. So curl of v for v equals PQR. Now, let me tell you, this is a little bit messier, PQR. This is not as fun. It's still going to be a cross product. So remember that the curl over here had something to do with determinants. Determinants are related to cross products. So let me just write if sometimes we call this operator is del. So this is partial x, partial y, partial z. Okay. And the definition of curl of a 3-dimensional vector field is essentially the cross product of that del operator with my v. So let me write this all out for you. Remember, to do cross product, you need a determinant with an I, a j, and a k up top. My del operator is partial x, partial y, partial z. And at the bottom, I've just got to supplement what my v is. So, and sorry, sometimes I put the hat on, sometimes I don't. Forgive me, sometimes I'll remember it, sometimes I won't. So we got P, Q, and R. If I write all of this out, I'm going to get a triple vector. And I've got to do, first I've got to do this minus this, okay? So I've got to do partial r, partial y, minus partial q, partial q, partial z. To get the middle one, I've got to do, what was it? It's this minus this. So it's partial p, partial z, minus partial r, partial x. And finally, for this last component, it's this minus this. So it's partial q, partial p, minus partial p. Sorry, that was crazy. No. Oh my gosh. I said that wrong. That would not make sense to talk about partial q, partial p. So we're doing partial q, partial x, and we're subtracting partial p, partial y. Now, sometimes did you just flip it? I may have, I think this is right. Let me think. Is there, oh, the j, you mean the middle one? Okay. Okay, remember on the middle component, you have to make that one negative. The middle one goes the opposite direction of which you think. You have to, yeah, that's right. Okay, good. Okay, good. So sometimes when people first introduce the curl of a 3D vector field, they just say it like this, and they say, oh, I expect my students to memorize that formula. No. So this is a much easier way. I mean, notationally, this is a better way to do it. In your homework, we only have a few minutes left, but so in this case, I need you to notice that the curl of V is also a vector field, right? Because it has 3 components, and those components are functions. So this is a vector field. Again, same notation. If curl of V is the 0 vector field, then we say V is curl free, or V is conservative. All right, and then okay, so I have a few minutes left. I can do, let's think. Actually, so let's do one last thing. I think I'll say this. I've got a couple different things I can talk about, but this is going to go back to Daniel's question from over here. This was that implication thing. Okay, this thing right here. I'm going to copy this and paste it. Copy. Okay. I'm going to kind of answer this question right here. Okay. So when does the second implication always hold? That is, let's say, i.e., suppose you compute that the curl of V is 0. Okay. Can you say a function, a potential function always exists? And the answer is only if the domain is simply connected. I know you don't know what that means right now, but the answer, this is huge. This is huge, and this is a beautiful, beautiful, beautiful piece of math that I study all the time. This is only if the domain of the vector field is simply connected, i.e., has no holes. Okay, and so I'll give a quick counterexample. So V of x, y, it's going to be negative y over x squared plus y squared, x over x squared plus y squared. The domain of this, I can plug in absolutely everything, except I can't make those denominators 0. So I can plug in everything but 0, 0. So can plug in all x, y, but not the origin. So the domain is not simply connected. The domain is all numbers except that hole at the origin. It's supposed to be a point removed. That is not simply connected. And this actually is, the curl of this V is equal to 0. Okay, so that's all the time that we have today. I'm going to stop recording.